Previously, I have looked at this problem in which my little yellow ball at a distance far away from Earth, at about 100,000 kilometers away from Earth, the center of Earth, fell onto the surface of the Earth, and I wanted to calculate the velocity of this ball on impact just before it hit Earth. So I've gone away and done this calculation. Let's just fill in the numbers. The potential at A, found using this formula, is minus 7.96 times 10 to the power of 5. Potential at B is minus 1.25 times 10 to the power of 7. Finally, after finding the difference between the two, which gives the E here, so decrease in potential energy, that's the E. Alright, subtracting them gives the E, and then solving this for the velocity gives 10,800 meters per second. So this is a huge velocity that the ball hits the Earth's surface. Now what I want to do now, let me just copy out this answer here. This the velocity that my little ball hits the Earth is 10,800 meters per second. So what I want to do now is this. I want to think about a slightly different situation. Suppose that instead of just dropping the ball, if I just drop the ball, it will just fall directly towards the center of the Earth, right? When it hits the Earth, it will hit at a right angle. Now suppose that instead of just dropping it, I give it a slight nudge, so that it just a tiny little nudge, nothing like 10 to the power 10,800 meters per second, just a tiny little nudge, so that as it falls at a slight angle, just a tiny little angle. I can give it a nudge, or I can just put it on a slight slope. Maybe put it through a tube that is slanted slightly, and it will just slide through the tube and fall at an angle. Okay, so I don't have to give it any energy at all. So it will slide and it will fall. Okay, it will start falling at a slightly different direction, and as it falls, okay, because it's not falling towards the center of the Earth, since the force of the Earth always attracts towards the center, it will curve slightly, probably. At first, it will be perhaps a bit straight, and then it will curve slightly, and then it will hit Earth. Okay, so that's where it hits. That's where it hits the Earth. Now, if you look at this situation, you see that perhaps let me exaggerate this a little bit. It will hit at a different part of the Earth, maybe somewhere there. Now, and you can see from this picture that it will clearly have traveled further, and it looks like it has fallen further. Now, we know what we normally expect when we drop something and it falls further, right? It will end up with a bigger velocity if it falls further. So this ball, when it falls and hits further away, what is the velocity here? what is the velocity of this ball that hits further away? Would it be actually bigger than the first one? Now the answer to this question is no. It will actually hit the surface of the Earth with exactly the same velocity as before, even though it has fallen further. Okay, that may seem strange. Now there are two ways to look at it. If you just look at the calculation alone, as I mentioned, the way to do the calculation is that we find the potential at A, potential at B, and then we subtract it to find the kinetic energy. So the calculation means that if I find the potential at this new point where it hits the Earth, that new point, although it's in a different part of the Earth, it is at the same distance from the center of the Earth. So it should give the same potential energy as this point, as the point B, because the potential energy is calculated with the same formula that depends only on R. So that's from the calculation point of view. But physically, we need to understand why. We should try and understand why, even though it falls further, it ends up with the same potential energy change and the same kinetic energy. Okay, because that's not what we might easily expect. And the reason is this. The way it works is this. Let me look at this motion. Now, in this motion, you can see that as it falls, it is under a force from the Earth, and this force acts directly towards the center of the Earth. Okay, acts directly towards the center of the Earth. Now, the reason why it doesn't fall in a straight line towards the center of the Earth is because this slight angle in the beginning gives it a slight component of velocity sideways. So that's why this sideways velocity or momentum carries it at an angle. So as it falls, it continues to have this sideways component of velocity, but it is the force towards the center of the Earth that causes it to accelerate, to increase in velocity towards the center of the Earth, all the time keeping this sideways component, which is why it goes at an angle. Now, so it is this component of the velocity, is this force towards the center of the Earth that causes the kinetic energy to increase, that actually does the work. So as it falls, it may end up on a different side of the Earth, but no matter what the angle of the motion is, the force on the ball at any point along its motion is always directed towards the center of the Earth. Okay, so it is the displacement towards the center of the Earth that contributes to the work done by the gravity on the force. So if you think of it this way, if you think about the definition of work done is the force times the displacement in the direction of the force. So then we can begin to have some idea why this sideways motion does not actually contribute. So let's complete the picture this way. Now think about this displacement. This is a curved path. Okay, so it's not a straight line displacement, it's a curved path. But we can still think about resolving this this curved path of displacement into two components. Just imagine one component which is directly towards the center of the Earth, and another component that is sideways. But this is not a simple straight line thing. So what I'm going to do is this. My towards the center of the Earth component, let me start from here at this point. If I want to think about the component towards the center of the Earth from the final point, let me think about drawing a straight line from the center of the Earth to the final point, and I'll extend it outwards. Okay, extend it outwards to there. So that's the direction of the force when it's here. Now, then let me think about this motion. Not motion, but let me think about a component of the displacement which is perpendicular to the radius from the Earth. Now, if I want this component to be perpendicular to the radius all the time, I have to draw an arc. Right? Only on an arc you will have every point of the arc perpendicular to the radius. So if I imagine resolving this displacement into these two components, right, one that's always perpendicular to the gravitational force, another one directly towards the center along the gravity, then you can see that if I imagine moving this ball this way, then along this path, no work is done by the gravity, because the gravity is not acting along this direction. Okay, if I want to move it from there to there, I have to use my own force to move it. Okay. Then, from that, it is then allowed to move along this direction towards the center. The Earth's gravity can start doing the work and pull it down all the way to this final point. So, because of this, we can think of it this way, that the work done when the Earth pulls it from there to there is the same as the work done if it moves by the Earth if it moves this way instead. Okay, it is just that this is the component along the direction of the force. So because of this, there's no work done along this component of the displacement that's perpendicular to the force. So therefore, if you just look at this motion, it is just the same as the previous motion that we did last time, but in another direction, but they are symmetrical. And this explains why the velocity, when it comes in at an angle and even when it falls over a bigger distance, ends up to be the same value as before. So what this means is that it makes calculation of such problems quite convenient, because no matter how it moves, whether it falls straight towards the center or whether it goes and then in a curved path or whether it travels in orbit around the Earth, it really doesn't matter. If we want to find the change in kinetic energies or potential energies, all we need is to use this formula. Regardless of where the point is or how it has moved, all we need is its distance from the center of the Earth to find the potential energy, and all we need is to calculate the difference in potential energy between any 2 points to calculate the change in kinetic energy.